In the azure glow of our galaxy, the mystical door is opening wide. In the cosmic factory, where the world unfolds, shining stars are being crafted. Stars, tiny seeds of miracles, blossoming in the folds of time, dancing in the radiant symphony of life. Yet, even in the darkness, stars that have lost their light are weeping. We must seek out those stars. I want to know why the stars have disappeared. Why have imperfect beings lost their light? In the cosmic factory, stars bear our dreams and hopes, but darkness is sweeping them away. In the factory of stars, efforts are made to create better stars for us. We must reclaim that light. We must seek out stars that should not exist. Those stars threaten our existence, yet there must be reasons behind their existence. Unveiling the mysteries of the cosmic universe, embarking on a journey to reclaim the light. Beneath the canopy of a single starlight, we will all find each other. Subscribing and liking greatly empower the creation of content. Hello. Today, I will provide a detailed explanation about our galaxy. Our galaxy is a vast collection of stars known as the Milky Way, to which our solar system belongs. The galaxy is also referred to as the Milky Way. The origin of our galaxy dates back approximately 13.8 billion years to the time of the Big Bang. The Big Bang is considered the birth of the universe, during which the incredibly small universe rapidly expanded, leading to the formation of energy and matter. Some of this material eventually contributed to the formation of our galaxy. Our galaxy is characterized by its distinctive spiral shape, with a flat disk and spiral arms extending outward from a central bulge. These spiral arms, known as the spiral arms, radiate from the central hub. The Milky Way is home to around 100 billion stars and rotates around the center, known as the Hubble plus 120 center, driven by gravitational forces. The Milky Way consists of various components, with stars and dust being among the most prominent. The galaxy hosts stars of varying sizes and shapes, all held together by gravity. Dust consists of tiny particles generated in space, and a significant amount of dust exists within our galaxy. Additionally, the Milky Way contains gas, and a central region known as the Hubble plus 120 center. Our solar system is located in the Milky Way galaxy. In reality, our solar system is situated toward the outer edge of the Milky Way. Moving from this outer region toward the center of the galaxy, there are various celestial objects beyond our solar system. However, due to the vast distances involved, these objects have minimal impact on our solar system, which remains relatively stable in its orbit. As for the future of the Milky Way, accurate predictions are challenging, but astronomers anticipate that our galaxy will continue to expand as part of the evolving universe. Furthermore, approximately 4 billion years from now, a collision with the Andromeda galaxy is predicted. This collision will eventually lead to the merger of the two galaxies. Alpha Centauri refers to the brightest and largest galaxy among the satellite galaxies of our Milky Way. The Alpha Centauri of our galaxy is known as the Large Magellanic Cloud, LMC, situated approximately 160,000 light-years away from Earth. The Large Magellanic Cloud is a much smaller spiral galaxy compared to our Milky Way, with a diameter of about 14,000 light-years and an estimated 100 billion stars. The gravitational influence of our Milky Way has caused the Large Magellanic Cloud to distort and stretch, forming many regions where new stars are born. Visible to the naked eye in the southern hemisphere, it is renowned as the brightest galaxy in the night sky. The Alpha Centauri system includes Proxima Centauri, which is part of our Milky Way. Proxima Centauri, a red dwarf star, is the brightest and largest galaxy among the satellites, forming the Alpha Centauri system alongside the large Magellanic Cloud. Proxima Centauri is significantly smaller and fainter than the Sun, and is the closest star to Earth after the Sun. Proxima Centauri is known for its variability in brightness due to its flare activity and emits strong X-rays. Within the habitable zone of Proxima Centauri, a potentially habitable exoplanet called Proxima b has been discovered. The term Betelgeuse giant planet refers to the possibility of the existence of a massive planet around Betelgeuse, a red supergiant star. Betelgeuse is the 8th brightest star in the night sky and corresponds to the shoulder of the Orion constellation. It is about 1,000 times larger than the Sun and located approximately 550 light-years away. Giant planets are typically composed of gases or ices rather than rocks, and examples from our solar system include Jupiter and Saturn. The presence of a giant planet around Betelgeuse has not been conclusively proven. However, some researchers suggest that the sudden decrease in Betelgeuse's brightness may be attributed to the passage of a giant planet. For instance, a research team analyzing data collected by Japan's meteorological satellite Himawari 8 from 2017 to 2021 discovered that the brightness decrease of Betelgeuse repeats with a 400-day cycle. They proposed that this phenomenon could be explained by the shadow of a giant planet orbiting around Betelgeuse. Research on the Betelgeuse giant planet is still in its early stages, and more accurate observations and modeling are required. The study of Betelgeuse's characteristics and the planet formation process is expected to contribute to a better understanding of these phenomena. There are many fascinating planets in our Milky Way galaxy with diverse characteristics. For example, 55 Cancri b, one of the closest exoplanets to the solar system, located about 40 light-years away. This planet orbits a G-type main sequence star that is approximately 25% larger than the Sun. With a mass roughly 8 times that of Jupiter, 55 Cancri b is a giant gas planet composed of hydrogen and helium. Due to its surface temperature of about 2,000 degrees Celsius, it is suggested that carbon on the planet might crystallize into diamonds, forming part of its structure. HD 189733b, referred to as a hot Jupiter, this planet is situated about 63 light-years away from Earth. It orbits a K-type main sequence star that is about 13% smaller than the Sun. With a mass approximately 1.1 times that of Jupiter, HD 189733b has a surface temperature of around 1,000 degrees Celsius. It is known for having glass particles in its atmosphere, leading to the speculation of glass rain on the planet. PSR B12557 plus 2b. This planet orbits a pulsar, PSR B1257 plus 12, which is the remnant of a star that underwent a supernova explosion, PSR B1257 plus 12b. This planet orbits a pulsar, PSR B1257 plus 12, which is the remnant of a star that underwent a supernova explosion. Located about 2,300 light-years away, this planet has a mass approximately 0.02 times that of Earth. Being the first exoplanet discovered in our galaxy, it is exposed to the intense radiation from the pulsar and is also known as a pulsar planet. I will provide an English translation for the information you provided about the factors that make certain star systems in our galaxy more likely to host extraterrestrial life. To search for extraterrestrial life, it is crucial to determine whether there are planets with environments conducive to life. Typically, conditions that would support life include appropriate temperature and pressure. Life forms find it challenging to thrive in extreme temperatures or pressure conditions that are too high or too low. Therefore, planets within a certain distance from a star, maintaining suitable temperatures and pressures, are considered within the habitable zone. This is also known as the Goldilocks zone. Liquid water, life as we know it, relies on water as a solvent for chemical reactions. Planets hosting life should have liquid water, as it is essential for various biological processes. This water can exist on the planet's surface or underground. Suitable chemical composition. Life forms are composed of specific elements, and these elements need to be available on the planet's surface or in its atmosphere. For example, life on Earth requires elements like carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, and others. These elements may be present through geological processes, atmospheric composition, or cosmic radiation. Star systems that meet the conditions for potentially hosting extraterrestrial life include Proxima Centauri, the closest star system to Earth, located approximately 4.2 light-years away. Proxima Centauri is a red dwarf star, much smaller and dimmer than the Sun. It has a known exoplanet called Proxima Centauri b, situated within the habitable zone. This planet is speculated to have liquid water and a potential atmosphere composed of carbon and nitrogen. TRAPPIST-1, a red dwarf star about 39 light-years away from Earth. The potential for liquid water and atmospheres rich in carbon and nitrogen is high on these planets, 3 of which are within the habitable zone. The potential for liquid water and atmospheres rich in carbon and nitrogen is high on these planets. Gliese 667c, a red dwarf star located approximately 23 light-years away, part of the Trinary system. Gliese 667, this star has 6 known planets, with 3 of them situated within the habitable zone. These planets are speculated to have liquid water and atmospheres composed of carbon and nitrogen. In addition to these, numerous star systems exist within our Milky Way, and some of them may harbor planets with conditions suitable for extraterrestrial life. Now, let me provide an explanation about black holes within our galaxy. Black holes are celestial objects with gravitational forces so intense that not even light can escape from them. They can form when stars undergo explosive events or mergers, and they come in various sizes and masses. In our Milky Way, there are several types of black holes, including Sagittarius Ortis A, a supermassive black hole located at the center of our Milky Way galaxy. Sagittarius A has a mass approximately 4 million times that of the Sun. Situated around 26,000 light-years away from Earth, it attracts surrounding gas and dust, forming an accretion disk. This accretion disk emits bright light due to high temperature and pressure, allowing observers to detect the outline of the black hole through this emitted light. X-ray binaries. It is estimated that there are thousands of small black holes in our Milky Way, most of which are believed to form binary systems with other stars. Black holes in binary systems absorb material from nearby stars, emitting intense X-rays in the process. Observing these X-rays helps confirm the presence of a black hole. For instance, the X-ray binary system GRS 1915+105, located about 6,000 light-years away from the galactic center, consists of a black hole with roughly 14 times the mass of the Sun and a companion star with about 0.8 times the mass of the Sun. Gravitational wave binaries. In our galaxy, there are binary systems emitting gravitational waves during the process of black hole mergers. Gravitational waves are ripples in space-time caused by the motion of extreme celestial objects like black holes or neutron stars. Through the detection of gravitational waves, we can learn about the existence and characteristics of black holes. For example, the gravitational wave signal GW1 FEMS 0914, observed in 2015, originated from the merger of two black holes with masses around 36 and 29 times that of the Sun, respectively. I will explain about supernovae and neutron stars that exist in our galaxy. Supernova. A supernova is an explosive event that occurs when a massive star reaches the end of its life cycle. This explosion is triggered by the collapse of the star's core under the force of gravity, ejecting the outer layers into space. The energy and material released during a supernova can contribute to the formation of new stars and planets. In our galaxy, it is estimated that about 3 supernova explosions occur per century. Neutron star. Neutron stars are dense remnants left behind after a supernova explosion. Composed almost entirely of neutrons, these compact objects typically have a mass about twice that of the Sun, but a size smaller than Earth. The density of a neutron star is comparable to that of atomic nuclei, and its surface gravity is approximately 10^11 times that of Earth. It is estimated that there are around 300 million neutron stars in our galaxy. Pulsar. Pulsars are a specific type of neutron star that rapidly rotates and emits intense beams of electromagnetic radiation. Pulsars can rotate hundreds to thousands of times per second, releasing particles at speeds close to the speed of light. These particles are channeled by the pulsar's magnetic field, creating beams of light. The rotation axis of a pulsar does not necessarily align with its magnetic axis, causing the beams to appear as if they are flashing when observed. It is estimated that there are around 200,000 pulsars in our galaxy, star factories in our galaxy, pillars of creation, and more. A star factory refers to a region where new stars are actively forming, predominantly found within interstellar clouds composed of gas and dust. These clouds undergo compression and heating due to the gravitational pull of stars, leading to the formation of protostars that eventually ignite nuclear fusion reactions. This process unfolds over millions to billions of years. In our Milky Way, numerous star factories exist, and here are some notable examples. Pillars of creation. The pillars of creation are part of the Eagle Nebula, captured in an iconic image by the Hubble Space Telescope, composed of interstellar gas and dust. These pillars stretch approximately 4 light-years in length. They are in the process of creating new stars, while being eroded by the light of nearby, recently formed stars. The pillars of creation are located about 7,000 light-years away from Earth and have been imaged in the infrared spectrum by the James Webb Space Telescope. Orion Nebula. The Orion Nebula is one of the most prominent nebulae visible in the night sky. Situated in the Sword of Orion constellation, it is approximately 1,500 light-years away and has a diameter of around 24 light-years. This relatively young nebula, formed about 100,000 years ago, is actively giving birth to new stars. Observations of the Orion Nebula have been conducted using the Hubble Space Telescope and the James Webb Space Telescope across various wavelengths. Carina Nebula. The Carina Nebula, one of the largest and brightest nebulae in our galaxy, is located in the Carina constellation. It is situated around 7,500 light-years away and has a diameter of about 200 light-years. Formed approximately 3 million years ago, the Carina Nebula is a stellar nursery where around 14,000 new stars are currently being born. Imaging of the Carina Nebula has been performed using the Hubble Space Telescope and the James Webb Space Telescope at different wavelengths. The Big Bang Theory posits that the universe originated from a point of explosion approximately 13.7 billion years ago. However, certain celestial bodies and observations seem to challenge or contradict aspects of this theory. By the way, these stars are found in space. For instance, in the Orion Nebula, over 150 objects were discovered drifting in space without a central star. These objects, estimated to be young and hot, with masses several times that of Jupiter, defy traditional theories of planet and star formation. Furthermore, some argue that while the cosmic microwave background radiation is considered strong evidence for the Big Bang, it can also pose challenges. The observed amount of lithium in the universe, derived from primordial nucleosynthesis predictions, does not align with theoretical expectations, creating a discrepancy. As anomalies emerge, the Big Bang Theory undergoes revisions, necessitating adjustments or supplementary theories. However, the absence of observational support for these proposed modifications poses a challenge. There are reports of unidentified ultra-high energy cosmic rays reaching energy levels deemed incompatible with current physics. These cosmic rays, if validated, highlight phenomena beyond the scope of contemporary understanding. In essence, celestial entities that defy expectations according to the Big Bang Theory serve as indicators of its limitations or inconsistencies. It's crucial to acknowledge that the Big Bang Theory is a hypothesis about the origin and evolution of the universe, and is not necessarily an absolute truth. Considering alternative possibilities remains an open avenue for exploration. Unexplained celestial entities beyond scientific expectations. In the vast cosmos, there exist peculiar celestial entities that defy conventional explanations, from theories like the Big Bang or stellar formation. Some examples include overweight planets, planets orbiting small red dwarf stars, but with sizes about 9 times that of Jupiter, challenging the theory that gas and dust in the protoplanetary disk are proportional to the star's mass. Quantum physics stars. Stars exhibiting both particle and wave characteristics, akin to electrons in quantum physics. Phenomena like interference patterns, observed in the double-slit experiment, manifest in stars, contradicting classical physics. Ultra-high energy spaceships, unidentified spacecraft with an energy level of 320 eeV, defying explanation within current physics. These celestial anomalies surpass scientists' expectations, questioning our understanding of the universe's origin and evolution. It underscores the limits of prevailing theories and beckons exploration of alternative possibilities. Quantum mechanics serves as a crucial tool in comprehending the internal structures of stars and the formation and evolution of the cosmos. This field, which studies the behavior of subatomic particles, provides precise explanations for phenomena that classical mechanics cannot elucidate. Quantum mechanics significantly influences diverse scientific and technological domains, such as understanding the properties of solids and the principles behind semiconductors. Quantum mechanics plays a pivotal role in unraveling the mysteries of star formation, evolution, and cosmic phenomena. By predicting and comparing aspects like a star's mass, temperature, and reactions, quantum mechanics aids in explaining various cosmic phenomena, including nuclear fusion reactions powering stars, calculating the lifespan and evolution of stars, and studying events like supernova explosions and black holes. Moreover, in cosmology, quantum mechanics is indispensable for exploring the initial conditions of the universe, the distribution of matter, cosmic expansion, acceleration, and the fate of the cosmos. Thus, quantum mechanics proves its significance across a spectrum of physics, from the microscopic to the macroscopic, providing insights that contribute to our understanding of the universe.